That's correct.
No, but he said for your section, he said tonight, 11:59.
But then he said like.
And then he said our section will also be through 11:59 Friday.
Yeah.
So he still hasn't changed it yet. Yeah, I'll show you the one that he was like. Like he recently just assigned it. Like, and it's I looked at it.
Those two questions. It's my boss. It's on midterms.
I don't know.
I just like the person with the beach chapter.
It's just for my job. Yeah.
How's it going?
No, it's part-time.
It's not seasonal.
No.
Oh, I thought you were saying you're doing this stuff like that. You're actually still
Yeah.
Normal. Oh, we're doing residence. You guys already did. The last thing you did was.
Is it only that you lost these?
Yeah.
You lost.
Same
right?
here.
Class, I can't understand.
It's like on too much information. Because he has like good reviews and
Because he's a good professor. But
it's a lot
I
of-
can tell you that although I did well on his final, he didn't.
There's more of you guys today than usual. You guys just have a midterm or something today?
No, so our classes from Professor Park,
Yeah.
we started in person.
Oh, I see.
So
Okay.
I think a lot of us are gonna have it after this class.
Oh,
Yeah.
okay, I see. So you guys are all going to that one.
Yeah, so
I see.
that's why.
I got you. All of you guys I'm seeing for the first time.
It's honestly bad. Yeah. 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 Oh, yeah. Oh. Yeah, almost done. Was the DM like 1, 2, or one is like more like concept, yeah. Yes. Two, yeah, it was 2 of them. Yeah.
I used to do Facebook. It was really
Especially when, like when you have to do graphs and all.
yeah.
Yeah. I stopped after entrance. It's pretty similar to, no, it's pretty similar to vibration. You have to do the possible. Boom. Yeah, it's pretty similar. Yeah.
All right, it's 2:30, so let's go ahead and get started. All right, good afternoon, everyone. It's good to have a full house for once, so this is really nice. So how's everyone doing today?
Pretty good.
Good, good. Hanging in there. It's cold. And yesterday it was raining, so hope you guys are staying warm and dry. Today we're starting something new, and so we're starting a set of lecture notes on transient heat conduction. And so I believe this is lecture note 04. And so my plan is to do it today, and then we're going to finish it up on Monday. Okay. And so I have some announcements before we begin. And so I think some of you have noticed this already, but homework 3 has been posted. I know you guys just got done with homework 2, but you know, it's this part of the class goes pretty fast, okay? And that's going to be due next Friday. Okay. And so a lot of the topics that's covered on that homework have to do with transient heat conduction. And so, you know, of course, we haven't learned it yet. And so you probably won't have everything you need to finish the homework until Monday. But after today, you should be able to get through a good portion of it. I would say after today, you should be able to get done with 75–80% of it. Basically, everything is up to the very last problem. Okay. So that's there. Okay. Next thing I want to talk about is the midterm. Okay, so we do have a midterm exam coming up. And so I know in the syllabus, I put a date for next Wednesday for our midterm, and we're not going to make it that day. And so I'm going to push the midterm back until the following Monday. Okay. And so the midterm exam will take place on Monday. And I was looking before this, so it should be Monday, March 7th. Okay. I think that's like 10, yeah, it's Monday, March 7th. Okay. So that's not next Monday, but the following after that. Yeah.
The homework still says due on Wednesday next week.
Oh, is it Wednesday? Oh, let me change that. So it should be due Friday because we need because you're definitely gonna need the lecture on Monday, and I want to give you a few days after that to do that. So yeah, that was a mistake on my bad. So it should be due next Friday. So we'll change. Okay, so regarding the midterm, let me just because I've already had a few questions on this, and so I just want to clarify kind of what my policies for the exams are. So, and so everyone knows we've talked about at the beginning, the exams are going to take place in person, and so everyone has to show up here during the exam. Okay. Okay. In terms of what you can bring to the exam, I use the same policy for all my exams where you can bring a sheet of notes. And so one 8.5 by 11 sheet of notes. All right, so you can use both sides, and so you can write on the front and the back. You can handwrite it, you can type it, either is fine with me. The only requirement I have for your sheet of notes is that you should be able to read it. And so, no magnifying glasses or no any weird viewing instruments or, it's all, if you can read it, without any trouble, that's fine with me. But besides that, you can put anything on that sheet of notes, okay? So sometime next week, probably early next week, I'm going to put out a study guide, probably on Monday. Right, so I'd like to put the study guide out about a week before the exam, just to help you guys with studying. Okay. And one thing I've been doing recently, ever since the whole Zoom virtual teaching, is I've been doing a recorded review video. Okay. Okay. So what I like to do is I like to use Zoom and I record usually about an hour-long video, just reviewing some of the core concepts for the exams. So unfortunately, an hour is not enough to cover, everything we've covered so far, because we've been covering a lot. And so what I do is that, probably next Wednesday, I'll put out a poll on Canvas for you to vote on which topics you feel most uncomfortable with in the class so far. And then based on probably the top 2 topics, I'm going to cover those in the review video. Okay. And so you can look forward to that review video being posted next Friday to help you study over the weekend. Okay. Okay, I think that's all my announcements. And so are there any questions on the I know there's some questions on the homework, but maybe we'll hold off until after the lecture today. I think today's lecture will help answer some of those. But are there any questions on the midterm format or the date or anything like that? Yeah. Both sides. So you can use both sides. Yeah. Mhm. Yeah, so the reason I do the notes is, I think, you guys are all at this age now where, I think you guys are beyond the age of having to memorize formulas and stuff like that. And so, the sheet of notes is there for you to write down those formulas so you don't have to memorize anything. To me, it's more important that you understand the conceptual information about how it all kind of pieces together, and kind of just the straight up memorization. I don't want that to be the bottleneck for you guys in this class. And so that's why I give you guys the sheet of notes. But also just writing the sheet of notes is a great study tool as well. And so kind of naturally just knowing that you only have just one sheet of paper front and back, you naturally kind of have to take all the information we've learned so far and condense it into that sheet of notes. And so that already is a great study tool. So what I've seen people do in the past is I've seen people take the homework solutions and the lecture notes and just shrink it really, really tiny and just print it all the way across on the sheet of notes. But I will tell you that 10 out of 10 times that approach is not successful. Because what ends up happening is that, yeah, you have all the information in front of you, but you spend more time kind of like trying to read it and trying to find the information than you do actually taking the exam. And, the exam itself actually takes some time. So you have to do some calculations, you have to do some thinking. And so, actually spend some time to actually condense the information, put it on your sheet of notes in a format that you can understand. I think that'll set you up really well for the exam itself. All right, questions. So can we use 2 sides of the sheet of notes or just one side? You can use both sides. Yeah, you can use both sides, front and back. All right, any other questions before we jump into the lecture today? Okay, all right, so let's go ahead and get started. Okay, so the topic that we're going to cover today and next Monday is known as transient conduction. And so if you've heard the word transient before, you should know that it means something that's temporary or something that changes with time. Okay, and that's going to be the whole theme of the lectures today and for Monday as well. Okay, so let me start off by saying that up to this point, we've always made the assumption that our situations are steady state. Okay? Okay. And so what that means is that our temperatures do not depend on time. Okay. For time, remember, we usually give that the symbol little t. Okay. And so for this week, we're going to relax that assumption. So we're going to look at situations that do change with time, but we're going to make some other assumptions as well, just to make sure the problems are actually solvable. Okay. So, and so when do these situations come up in practice? Okay. And so in practice, these situations occur whenever something in the environment or something in the thermal environment is either changing very quickly or changes very suddenly, or just otherwise just changes with time. Okay. Okay. Right. And so now that we're assuming that our temperatures change with time, it kind of fundamentally changes, what we're going to be looking for in our problems, right? Because up to this point, we've covered planar conduction, we've covered radial conduction. The temperature has always been a function of some kind of space variable, right? Whether it be x, whether it be r, right? And so x and r, they're both spatial variables, so they denote kind of a point in space. For this unit, we're not looking for temperature distributions anymore. We're going to be looking at temperature time evolutions. Okay. Okay. And so no longer are we going to solve for t of x. We're not going to be solving for t of r, right? Now we're going to be solving for t of t. Okay. And so it might seem like a very minor kind of notational difference, right? And so, we're still solving for temperature, but instead of x and r, instead we're doing t. But time is kind of a very fundamentally different thing than space. Okay. And it changes the equation that we're going to use as well. And so to solve for these time evolutions for temperatures, we're going to need a whole nother method to use. It's not super different, but it has a name. And so the method that we're going to use is known as the lumped capacitance method. Okay. Right. And so the reason we have to use this method instead of just solving up the straight up heat equation is, you'll see once we start doing some examples that, we have to make kind of a very key assumption here that we've never made before, because otherwise these problems become a little bit too hard to solve. Okay. But some situations that might occur for this, we'll do an example later of something maybe you see every time you go to a restaurant. You take like an ice cube, you take the ice cube and you put it into your drink, right? And so over time, what you expect to see is that ice cube is going to heat up because it's going to absorb some heat from the drink or some heat from the surrounding area, and the ice cube is going to melt. Okay. And so with the lump capacitance method, we're going to be equipped to handle those situations that change with time. Okay. All right. Any questions on this so far? Okay. All right. So let's do a kind of the opposite example. Okay. And so the opposite example here is that we have a very hot object, and so we'll say that's like a very, you take like a very hot piece of metal, and we're dunking it into a water bath. Okay. And so here is our drawing. And so, part of this assumption is we're going to assume the water bath is really, really big. Okay. And then inside of this, we're going to dunk our piece of metal. Okay. So there's our metal, and it's really, really hot. Okay. And so let's go ahead and label some of these things. So this is water. This right here is a hot piece of metal. Okay. The water has a temperature T infinity. Okay. And the object, the metal here, has a temperature T. Right. And instinctually, we know that it's going to be a function of time, right? And so if you take out a hot piece of anything, and you dump it into a cold water bath, you know that that hot piece of something is going to cool down eventually, right? And so we can kind of already say from the start that this temperature here is going to change with time. So that's why I have T as a function of little t. Okay, so what are the assumptions that we're going to make? And I should have listed this earlier because this is an assumption of the lump capacitance method in general. Okay. The key assumption that we're going to make here is that the piece of metal has a spatially uniform temperature. Right? In other words, if you measure the temperature at any point on that piece of metal, it's going to be the same. Okay. Okay. So another way that you can say it is the entire piece of metal is the same temperature all throughout. Okay. And so in a sense, this is kind of the opposite assumption that we made before, because in the past, when we looked at steady state situations, we assumed that the temperature didn't depend on T and instead depended on some spatial variable. Here we're doing the opposite. And so we're assuming that the temperature doesn't depend on space, but instead only depends on time. Okay. And so that's going to be key because otherwise we wouldn't be able to solve these problems. Or I shouldn't say that. You can still solve them, but it would be a lot more difficult to solve those. Okay. Any questions on this so far? Yep. Yeah, it's a good question. So the question is, would the water's temperature T infinity also be a function of time? That's kind of the other implicit assumption that we're making here. And that's why I drew the water bath to be really, really big. Normally, if you have kind of a smaller water bath, then yeah. And so any heat that leaves the object is going to heat up the water as well. But because we're assuming this water tank is really big, then it almost acts like a reservoir. And so any heat that comes into it, it's not going to make any impact on the overall temperature. Yeah, good question. We can actually go ahead and list that as an assumption. That's a good point. Okay. Okay. All right. And so, again, so instinctually, what we expect to happen is that the hot metal will rapidly cool down until it reaches the temperature of the fluid. Okay. There's two L's, two C's in there. Oh well. Okay. And so our solution for T of T should reflect this. And so we expect our T of T to kind of, to rapidly decay quickly, and then maybe it'll level off in the end. All right, and so to derive the equation that we're going to use to solve this, we're going to draw a control volume around the metal. And so in other words, we're going to make an energy balance around the piece of metal. Okay. Okay, so there's our piece of metal. Looks like Mr. Potato there, okay? And so what we know from the, just kind of what we physically expect, right? Heat is gonna leave this, this piece of metal, okay? And since, we're going to assume that the piece of metal is kind of slowly dropping in the water, what we're gonna say is that all of the heat transfer that comes out is gonna be due to convection, okay? Okay. Which we have an expression for. And so we know that the heat transfer due to convection is equal to H times A times the temperature of the object minus the temperature of the fluid. Okay. And so that's how much heat is entering the fluid due to convection. Okay. But due to conservation of energy, we know that that energy has to come from somewhere, right? So that energy just can't be spontaneous. And so where that's coming from is due to the fact that the piece of metal itself is losing internal energy. Okay. And so what we can say is that the rate at which the piece of metal is losing energy, or the rate at which its internal energy is going down, is equal to rho times V times C times dt. Okay. And so this is the rate at which object loses thermal energy. Okay. And so as the piece of metal rapidly cools down, then the heat that comes out because of that is being lost due to convection. Okay. Okay. And so due to the energy balance that these two, because of conservation of energy, these two quantities have to be equal. Okay. Okay. Right, and so if we set these equal to each other, and I'm going to put a minus sign for this one just because it's energy coming out. Okay. And so if we set these equal to each other, then we have rho V C dt is equal to minus H times A times T minus T infinity. Oh, I never defined what those terms mean. I'm sorry. Let me define what each of these terms on the left here mean, because we haven't seen some of these in a while. Okay. And so the rho here is density. And this V here is the volume of the object. Okay. And the C here is the heat capacity. And so the heat capacity is a property of the material that the object is made out of, and it basically states how much a certain mass or certain amount of that material can hold. Okay, and so certain materials are better at holding heat or retaining heat than others, and so the heat capacity reflects that. Okay. Okay. But for mathematical purposes, we're going to assume that all of these are constant. Okay, so we're going to assume the density is constant. We're going to assume the volume is constant, and you might get a little bit of shrinkage. I know, especially if you have rapid energy differences or rapid temperature differences. Especially if it goes down, the object's going to contract. But we're just going to neglect that at this point. And so we're going to assume the volume is constant. Heat capacity is of course constant, and H and A are going to be constant as well. Okay. And so what do we have here? And so just by this energy balance, what we have is we have a differential equation, the first order one. Okay. And so we can take this differential equation here and solve it for t as a function of t. Okay. Okay. All right, so let me pause here and ask, are there any questions on this so far? Okay, and so we have this equation here, and it came about just as a straight up energy balance. Okay, and so now what we're going to do is we're going to solve this equation for t. Okay, but before we do that, I'm going to do a something just because we're usually lazy, and if we can avoid doing math, then that's usually a good thing. And so I'm going to bring up an old friend from our last unit on fins. Okay. Right, and so I'm going to replace t with theta. Okay. Remember, theta here is equal to t minus t infinity. Right. So do you remember this guy from our fins unit? And so this theta here, remember, is known as the excess temperature. Okay. And so in other words, it represents the temperature that's in excess of the fluid being considered. Okay. And so this is nice because if we assume that T infinity is a constant, when we take the derivative of this, we see that theta dt is equal to dt dt. Okay. And so if we plug that expression in there, we have rho Vc times d theta dt is equal to minus HA theta. Okay. And so this equation here is a little bit easier for us to solve. Okay. Because now we have this equation is homogeneous, and even more nicely, this equation is separable. Okay. So do you guys remember how to do separation of variables for ODEs? It's okay. I probably forgot it at this point too. So we'll review how to do that. Okay. And so we can solve this with separation of variables. Okay. All right. And so what we're going to do is we're going to take rho Vc, and we're going to divide it on both sides of the equation. And so it's basically going to end up on the denominator here. Okay. At the same time, we're going to take theta, and we're going to divide it by both sides of the equation. So theta is going to end up on the denominator here. Okay. And then the dt, thankfully we're in engineering because this is kind of a mathematical abomination. And so the math department will murder us for this. But we're going to move this dt over to the top here. And so we're kind of multiplying both sides by dt. Personally, I don't see what's wrong with it, but every time I show this to my math friends, they just cringe, and I see their souls leave their body for a couple reasons. Okay, and so we do all that math, we end up with d theta over theta is equal to minus HA over rho Vc dt. Okay. So in other words, we've separated out the variables. Okay, so we put all the theta terms on one side, and we put all the other stuff, everything that's not theta, on the other side. Okay. And so at this point, we can integrate. Okay. And so on the left-hand side, we have d theta over theta. And so we have the integral of 1 over theta, basically. And so this is going to be natural logarithm of theta, right? Next, we have integral of HA over rho VC. And so since all of those quantities are constant, and so we're basically just integrating a constant number. And so all we're going to end up with is a T right there. Okay. And since we're doing an indefinite integral, just like we've done in the past with our heat conduction units, we have to add an arbitrary constant C. Okay. Okay. Any questions on how we got to this point so far? Okay. All right, so let's go ahead and keep massaging this. Okay, and so right now we have ln of theta on the left-hand side. And so we want to get that to be kind of just straight up theta. And so to get rid of the ln, I'm going to raise both sides to the e power, okay? Or e to the power of that. And so on the left-hand side, I have the e is going to cancel out the ln. And so we have a theta of t. Okay. This is equal to e to the minus HA all over rho VCT plus C. All of that is in the exponent. Okay. And if you guys remember your exponent rules, that if you add something in the exponent, it's like you're multiplying it together, right? And so this is the same thing as e to the minus HA over rho VCT multiplied by e to the C. Right? And so since C here is an arbitrary constant, we haven't specified its value yet. We can kind of replace this with another constant just to make it a little bit easier for us. And so what we can say is that instead of e to the C, I'm going to replace this with an arbitrary constant A. Okay. And so if we do that, we have theta of t is equal to A e to the minus HA or rho VC t. Right. And so that right there is our general solution to our equation. Okay. And so we have an exponentially decaying term, and I'll show you what the ramifications for that are in a second. And we have our arbitrary constant A. Okay. All right, and so at this point, we know the drill, and so whenever you have an arbitrary constant in your solution function, we need to apply some kind of condition to solve for its value, right? And so previously in our heat conduction or steady state conduction examples or steady state conduction problems, we applied boundary conditions. But in this case, since we have a time dependent system, we're going to apply what's known as an initial condition. And so it's a different name, but mathematically it means the same thing. Okay. And so in other words, we need to apply the condition when t is equal to 0. Okay. All right, and so for this particular problem, we're going to assume that when t is equal to 0, that's when we first dunk the piece of metal into the water. Okay, and so that's basically when the temperature of the metal is going to be the hottest. Okay. Okay. And so basically, we're going to be making the assumption that we know exactly what the initial temperature of the metal is, right? And so this Ti right here, this is initial metal. Okay. All right. And so, physically, what you can kind of describe this as happening is, we heat up the metal, we know how hot we heat it up, and then at its peak of heatedness, then we dunk it into the water bath. Okay. And so this gives us our value for A. So if you plug in 0 into this expression, and so we end up with e to the 0, we know that the exponential of 0 is just 1, right? And so that gives us A is equal to theta I. And so if we put it all together, our full solution full with two L's. Our full solution is theta of t is equal to theta I e to the minus HA over rho VC t. Okay. All right. Any questions on this? Okay. All right, so let's plot this. And so, if we kind of scroll back up in these notes, what we kind of physically expect to happen. Question. So do we care if we solve for theta t like math majors do? What do you mean like math majors do? You mean if you have a different way of solving this than separation of variables? Yeah, that's okay. Yeah, as long as you show all your work, then that's fine. Yeah, as long as you end up getting the same answer, then you can use anything you want, except for Wolfram alpha. So don't no Wolfram alpha or no none of that. So as long as it's as long as it's work that you can track and I can see all your work, then that's anything is fine. Yeah. Okay. So let me plot this. All right, so if you remember, when we first started solving this this problem, what we kind of said at the beginning was that what we expect to happen is that right when we dunk the piece of metal into the water, then the temperature should rapidly decline. Right? So it should go down very, very quickly. Okay. And so if we plot this, you can see that's exactly the case. So when t is equal to 0, of course we have our initial temperature difference here. Okay. And if you know what kind of a decaying exponential looks like, it looks something like this. And so a decaying exponential, what it's known for is a very rapid early decline. Okay. And then later on, it kind of, the time evolution kind of tailors off. And so this mathematical result here is kind of, basically exactly what we expect from this solution. Okay. All right. And so that's great. And so, the mathematical solution that we got is consistent with what we physically expect to happen, which is always a good thing, whenever you're dealing with these kinds of analysis. So let's dive a bit deeper. Okay. And so in particular, I want to look at this quantity right here. And so, if you kind of remember from your previous math classes, a lot of times you've probably dealt with these exponentials, either decaying exponential or a rising exponential. And so this quantity that's kind of the coefficient in that exponential, this is what's often known as the time constant. But for now, I'm just going to call this the exponential coefficient. Okay. And so we have HA all over rho VC. Okay. Okay. And so what I'm going to do here is I'm going to examine each term in the numerator and the denominator, and we're going to look and see how they affect the thermal thermal time evolution. Okay. So let's start with H and A. Okay. So H and A, remember H here is the convection coefficient. Okay, and A here is the surface area of the object. Okay. And I'm grouping these two terms together because you can see that they're both in the numerator of this coefficient, right? And so what happens, if we look at this curve right here, And so what happens when either of these go up? Right? And so let's say that we increase the convection coefficient or we increase the surface area of our object. Right? And so if H or A goes up, okay, if these go up, then that's going to increase the rate of the decline, right? And so it makes the exponent bigger. And so if the exponent's bigger, it makes it decline faster, okay? Okay. And so if we draw kind of a companion curve here, and so if we have an H or A go up, you might have something like this. Right? And of course, the opposite is true too. And so if your H or A go down, right, then it's going to slow down the decay, right? And so you're going to have something that looks like this, maybe. Okay. And so it's going to have the same shape, and so eventually it's going to decay down to 0, but the rate at which it decays is going to go up or down, depending on H or A. Okay. And why is this, right? So both of these quantities here, both H and A, they have to do with either the strength or the efficiency of the convection. Okay. And remember, the only mechanism that we have for heat transfer coming out is convection. And so if we increase the strength of the convection, then of course heat is going to leave this object a lot faster. And if heat leaves the object faster, then it's going to cause the temperature decline more. Okay. Okay. Right. And so if you increase the amount of convection, you increase H somehow, then of course that's going to make the temperature drop faster. And same thing with the surface area as well. Okay. So these are kind of similar concepts that we talked about in the fin unit as well. But we're kind of seeing it in kind of a twist here for transient conduction. Okay. Any questions on this? Okay. All right, so now let's look at the denominator. And so the denominator, we have 3 quantities there. Okay. And so we have rho. Rho here, of course, is the density. V, we have volume. And C is the heat capacity. And these are all in denominator. Okay. Right, and so since all of these quantities are in the denominator, they're going to have the exact opposite effect as the 2 quantities that we looked above. Okay, and so let's look at the case if these go up. Okay. If these go up, then the opposite is going to happen, right? And so if these go up, then the denominator is going to increase, and the overall coefficient is going to go down. And so if these go up, then this is going to slow down the rate of decline. Okay. Okay. All right. And of course, the opposite is true if they go up, right? Or excuse me, if they go down. And so if you decrease the density or volume or heat capacity, then it's going to make the rate of decline go up. And so if we go back to our curve up here, right? And so this top purple curve, you can obtain that if you decrease H or A, but another way that you can obtain this is if you increase rho, V, or C, okay? And then conversely, for the bottom one, you can obtain that by decreasing rho, V, or C. Okay. And so there are kind of two ways to obtain the same result. Okay? And so why is this physically? So why is it that when we increase or decrease these, they have the opposite effect as H and A? Okay. And so all these parameters here, they all kind of contribute to the same thing. And so, together, this is what's known, this product of these three quantities together, this is what's known as the thermal capacitance of an object. And so I'm going to bring another analogy to circuits. And so if you think of a capacitor in a circuit, what does a capacitor do? So a capacitor is known for storing electrical charge, right? Not in the same way that a battery does, but it can temporarily store some electrical charge. And so in the same way, what these quantities do, they let you know how much thermal energy this object can store. Right, and so if you look at each of these quantities, it makes sense, right? And so, if you have, let's look just at the most obvious one. You look at volume, right? And so if the volume goes up, then you just have a bigger object, right? And so bigger object, of course, is going to be able to store more thermal energy, right? You have density, right? So a more dense object is more densely packed with more molecules. That's kind of what density means. And so if you have more molecules, then those molecules are going to be able to store more thermal energy as well. Okay. And heat capacity is kind of in the same thing. Okay. So higher heat capacity means more thermal energy storage. Okay. Okay. Any questions on any of this? Okay. All right. And so I do have another example with an ice cube, but I want to make sure I cover the Biot number because that's a big part of your homework. So let me do that one first, and then if we have time, then I'll go back and do the ice cube example. Okay, so now that we've kind of gone over what the lump capacitance method is, right, and kind of we've dissected kind of the mathematics behind it, let's kind of take a step back and say, and ask ourselves, when can we apply this? Okay. Right. And so if we go back to kind of the beginning of this problem, we made a couple key assumptions. But let's focus on just the first key assumption that we made was that we assumed that the object was the same temperature all throughout. Okay? And so a fair question to ask is, when can we assume this? And is there a way to kind of test, right? Is there a simple calculation that we can do to test whether this assumption is valid? Okay. Okay, and so to test this assumption, let's kind of bring it back to an example we've seen before. Okay. And so let's examine the case where we have a planar wall. Okay. And so let's say the length of this wall, the thickness of the wall is L. Okay. Right, and so the wall has a thermal conductivity K. Okay. And let's assume that the cross-sectional area is A. Okay. And let's assume that on the outside of the wall we have convection. Okay. So this is going back to our planar case, right? And so we have a planar wall, with planar convection. Okay. Let me write out the formulas that we have for the conduction resistance as well as the convection resistance. Okay. Okay, so for the conduction resistance, remember for a planar wall like this, it was the thickness of the wall divided by the thermal conductivity multiplied by A. Okay. Whereas the convection resistance is the 1 over H, which is the convection coefficient, multiplied by A. Okay. And so this is all, pretty standard stuff, right? So we have a conduction resistance, convection resistance. Okay. Let me take these two expressions and do something we haven't done before, which is take the ratio between them. Okay. And so let's say that we take the ratio of the conduction resistance and the convection resistance. Okay. All right, so let's go ahead and mathematically work this out. And so this is going to be L over Ka. And we're going to multiply this by 1 over the convection resistance. And so this is, we're going to have 1 over H times A. And so we flip the we flip the denominator on its head, and so we end up with just HA. And so of course our two areas are going to cancel out, and what we end up with is H times L divided by K. Okay. All right. So a couple things to note before I give this a name, right? Since this result here was born out of a ratio, right? So we took the ratio of a resistance over resistance. That tells us that this quantity here is going to be unitless, right? And so it's not going to have any units. Okay. And so whenever you see a unitless number in applied sciences, applied math, it makes you think that it's going to be some kind of non-dimensional number. Right? So remember those from fluid mechanics, you had things like the Reynolds number, and I'm blanking. You probably learned some other ones too, but there's a lot of them. Okay. Kind of as a side note, it's kind of an easy way for people to get famous as a scientist, and so you come up with some number and you slap your name on it, and then you're famous forever. Right. So Reynolds did that, of course, and then. It's funny because you read some of the scientific literature and other people have tried to do the same thing. And so they study like a very niche problem and they said, oh, I've come up with this non-dimensional number. I'll call it the Tran number. And then you expect people to catch on, but everyone just laughs at you because you try to name a number after yourself. Not speaking from experience, by the way. I was speaking for a friend. I'm going to say that. Okay, and so this particular number, this was discovered by some dude named Biot. Okay, and so this is what's known as the Biot number. And so the abbreviation for this is usually BI. Okay, but BI is short for Biot. Okay. And so, what does this represent, right? And so, of course, we can see the mathematical definition here. It's H times L divided by K. But the way that we obtained this was we took the ratio of basically how strong the conduction resistance was compared to convection. Okay. And so that's the definition of Biot number. And so Biot number represents the relative strength, or I say relative resistance of conduction versus convection on an object. And so that's kind of the conceptual definition of what the Biot number represents. Okay. All right. And so let's take a case for when the Biot number is small. Okay. Okay. And so arbitrarily, I'm going to say small is going to be less than 0.1. Okay. Okay. And so if the Biot number is small, what that tells us is that heat can travel, or the conduction resistance in the object is much lower than the convection resistance. Okay. In other words, what that tells us is that it's much easier for heat to travel via conduction than it is through convection. Okay. Okay. Right. And so if you have an object here, right? Okay. If our Biot number is less than 0.1, and so let's say that it is 0.1, okay? Then if heat wants to travel from this point, from the center of the object, out to the edge, right? So let's say this is Q. Okay. If we compare that to let's say that the heat is traveling the same distance, okay, out of the object, but the difference between these is that this is conduction, right? And once it leaves the object, it becomes convection. Okay. If the Biot number is really small, then what that tells us is that this part of the journey is at least 10 times easier, right? Or in other words, it faces 10 times less resistance when the Biot number is small. Okay. Okay. And so in other words, if the Biot number is really small, then this tells us that the heat's going to spread through really easily. Okay. So that's great for us, right? So remember, the reason we kind of started talking about Biot number was we wanted to see, when is it relevant to say that the object is the same temperature throughout. Okay. And so if we have a small Biot number, and that tells us that the heat can conduct a lot more easily, that's a pretty good indication that our temperature is going to, or our object is going to be the same temperature throughout. Okay. Okay. Right, and so with that in mind, this gives us our criteria for determining when the lump capacitance method is valid. Okay. Okay. And so mathematically, we can say it like this. And so if the BI, which is equal to H times L divided by K, okay. And so if we say that the Biot number is less than 0.1, then the lump capacitance method is valid. Okay. Okay. And so, if you come across an unsteady heat situation, something that's going to change with time, the first thing that you can do is you can compute this Biot number, and if that Biot number is less than 0.1, then that tells you that you can use the lump capacitance method. Okay. And the alternative to the lump capacitance method is a lot more work. And so, if you're going to use the lump capacitance method for an unsteady problem, that's usually going to be a good one. Okay. Okay. So a couple notes on this before maybe we'll go back. Maybe I'll just do a couple parts of that example. Okay. And so the key thing that's going to be difficult to compute here sometimes. So H is usually given to you in the problem, or it's there's a way to compute H. K is not that hard to find. So K is it's a property of the material. You just Google it or you look it up in a property table. Surprisingly, the thing that can be difficult to compute sometimes is L. Okay. Okay. And so as an example, let's say that you're sitting in a sauna, right? And you want to know if you can use the lump capacitance method on yourself to see if you can model how quickly your body temperature is going to go up, right? And so if you look at a human, what do you say is the length of the human, right? And so some might say the height, some people might say the width, some people might do something weird. And so it's unclear, okay? And so in cases when you have a complex object and the length that you should use is not clear, what you can use is what's known as a characteristic length. Okay. 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 And so LC, in the way that you can compute is you can take the volume of the object divided by its surface area. And so if you take that ratio of the volume and the surface area, that'll give you something in units of length, and that's usually something good that you can plug in, plug in for the Biot number. Okay, because a lot of times it's not clear sometimes for some of us. So if you're not sure what length to use, then that's a good one that you can do. Okay. Any questions on this? Okay, all right, so let me do, let's see, we have about 13 minutes left. Let me do kind of the big, I don't know if we have time to cover everything in this example, but I think it's a good one to kind of wrap up with, okay? let me just do kind of the highlights. Okay. Sports Center top 10 of this example. All right, so let's do the example that I talked about kind of really early in the class today. So let's say that you take an ice cube and you drop it into a large tub of your favorite drink, which is non-alcoholic. Otherwise, I'll get in trouble. So let's say it's a punch bowl. Okay. Here is our bowl of punch. Okay. Right. So your party guests are complaining that the punch is too warm. And so what you do is you say, here is how much I care about this problem, and you drop a single ice cube into the punch bowl. All right, and so here we kind of have an opposite situation as what we had before, right? So before we had a very hot object dropping into a cool fluid. Here we have the opposite. So here we have a cold object and we'll say an uncomfortably warm fluid. Okay. Okay. Right, and so in this case, we have T infinity, which is the fluid temperature. This is going to be greater than Ti of the object. Okay. 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 And so let's say for the ice cube, we know it's made of water, and so we know its density. So we'll say it's a rho W. We know the length of the ice cube. Okay. We'll say that the length is L. Okay. And we know its heat capacity. So that'll be heat capacity of water. Okay. Okay. And so let's say what we're interested in. All right. So first thing we can compute is we can compute the time evolution of temperature for the ice cube. Two, let's compute how long it'll take for the ice cube to start melting. And let's just focus on those two for now. Okay. Okay. So any questions on this? Okay. All right. And so even though we have kind of an opposite situation here, our previous solution can still apply, right? And so if you remember, right? And so this is assuming the lump capacitance method applies. Okay. And so let's say that we check the Biot number. I forgot to give you H. Well, there's no numbers in this problem, but you know, H is there. H is present. It's alive. Okay. And so if we computed the Biot number, you know, we're basically assuming that this Biot number is less than 0. Okay. Okay. And so that's what we're assuming. Okay. And so if we assume that, then believe it or not, then our other solution here is still valid. Okay. And so if you remember from our hot metal example, right, our theta T in that case was theta I which was the initial temperature difference between the object and the fluid, multiplied by E times minus HA over rho VC. Okay. Right, because everything else is exactly the same. So the only thing that's different is that the temperatures of the two objects or the two temperature of the fluid and the object are going to swap. Okay. And the way that manifests mathematically is that now instead of theta I here being positive, right? So remember, theta I is the difference between the initial temperature of the object and the fluid, okay? Right? And so before, when we had a hot piece of metal and a cool fluid, this Ti minus T infinity was a positive number. Now when the two are swapped, this now just becomes a negative number, okay? And so if you plot this, okay, it's now going to look something like this. Okay? So here's theta I, it's somewhere below 0, okay? But we still have this decaying exponential behavior that looks like that. Okay? Except now, instead of starting from above the x-axis, now it's starting below the t-axis, like this. Okay. But all the properties, all the h and the a's and the rho's and the v's are still valid. Okay. I guess the only thing that's different in this one is that instead of having an amorphous, blob of metal, now we have an actual cube. And so the volume of the cube is simply just the length of the cubed. Okay. And so that would be kind of the only difference that we have here. Okay. Because now that we have a defined shape, we can apply that defined shape into our formula. All right. Any questions on that? Okay. All right, so now let's do part 2 of the problem. So part 2 asks us to find out, how long is it going to take for the ice cube to melt? Okay. And so let's say that Tm, Tm is the melting point of water. Okay? Okay. And so if we say that Tm is the melting point of water, then what we can say is that we can define theta m. Okay, theta m being Tm minus T infinity. Okay. This is the excess temperature when the ice cube will melt. Okay. And so what we can do now is we could plug this in. We can plug this into our solution above for theta of t, right? Okay. And since it's asking us for a question of when, right? A when question will basically is asking us to solve for the time at which something takes place. Okay. And so for a question like this, where it's asking us, when is the ice cube going to melt? We know the temperature at which the ice cube melts. Now it's just using our result from the lump capacitance method to solve for that time. Okay. And so let's go ahead and plug that in. And so we have theta m is equal to theta I times e to the minus HA over rho VC, okay, multiplied by T. Right, so all I did was I just took our temperature solution up here and I plugged in theta m for theta of T. Okay. And so now what I'm going to do is I'm going to solve this equation for T. Okay. And so to start, let me divide both sides by theta I. Okay. And so on the left-hand side, we have theta m divided by theta I is equal to e to the minus HA rho VC T. Okay. Right. Since the t here is in the exponential, we need to get it out of there. And so the way that we obtain something from an exponential coefficient is we take the natural logarithm of both sides. So take the ln of both sides. And so of course the ln is going to cancel out with the e. And so we have ln of theta m, theta I is equal to minus HA over rho VC multiplied by t. Okay. I'm just writing down the step that we took. Okay. Right, so now that we have it in this form, we just have to move this part of the expression over to this side, and we can solve for t. Okay. And so t, and let me give it an indication here. So let me call it t sub m. T sub m is going to be equal to minus rho VC over HA times ln of theta m divided by theta I. Okay. And so that's the time at which the ice cube is going to melt. And so of course you would have to plug in for these values, but then that'll give you a number. Yeah.
Up towards the top of your screen, the exponent, the exponent.
Yep.
HA, is that negative PV, rho VC, or is that just like?
Oh yeah, it's just my failure at writing a parentheses.
Okay.
Yeah. So there's only one negative. It's out front. Yeah. Mhm. And of course, the negative here is concerning. And so, does that mean we're going to get a negative time? And so the negative here is just to cancel out because this number right here, this number here is going to be negative. Right? And so theta m is likely going to be less than theta I. And so if you take the natural logarithm of something that's less than 1, that's going to give you a negative number. So that negative number is going to cancel out with that negative, and you're going to end up with a positive number. Okay. All right. Any final questions before we wrap it up for today? Okay, all right, and so that's all we get time for today. And so on Monday, we're going to finish up the second half of these transient conductor notes. But just from today, you should be able to get a good start on the homework. Okay? And so this is the only time I'm seeing you guys this week, but hope you guys have a good weekend, and I will see you guys next week. Hey, Kevin, how's it going?
A little tired.
Yep.
Is there a specific reason of conduction over?
It's yeah, it was fairly arbitrary, but kind of the convention for Biot numbers that we look for Biot numbers that are less. So that's kind of the reason for conduction over convection. Because like ultimately we want the condition which we want a condition where it says that conduction is much bigger than convection. But it was fairly arbitrary. So you could do it the other way. So if you define the Biot number as like convection over convection, and instead you'd be looking for large Biot numbers.
Yeah.
But since this is just kind of how it's defined. There should be one next to the elevator. I'm not in this building all that often, but it should be right there. Yep.